the description for fifth work.
Yeah. So what I want you to do. So we have already a recording where I explain how school risk 5 works in basics, graphics, music, the, the repository, and like many of the participants on the call, they like either saw this example working in a repository, basics, graphic, music, uh, or they took part in a seminar. So Nargiz took part in a seminar which where we implemented school risk 5 in a system Verilog homework. So now what I want you to do, I want you to share the screen with your version of system Verilog homework repository, and describe from the start, starting with a baseline school risk 5 example, just like telling what like different sub modules are doing, and then you can describe the first task, which is adding multiplication instruction using combination or multiplier. And then I want you to discuss adding combination, like adding multiplier with the latency, and then to describe all other tasks. So just to present to us all the solutions. So we will keep this recording and show it to students who want to check their answers later on. And after you like uh, finish your presentation for your implementation of multiplier with the latency, I will show a solution from a student who was interviewing to Samsung and who got an offer. So he has a solution which actually implements pipeline uh, with bypasses and forwarding, and then I will describe an idea how to create an example which shows like all stages, how you add like stall, pipeline, bypasses to this version of school risk 5 with uh, with a multiplier with the latency. Uh, and then I want you to describe fetch with latency and sharing a common memory by several CPU cores. In other words, I want you to now just describe the solution, and we will keep this recording, and later on we can show to students uh, like like after their homework is checked, we can show this to the students for like additional check and review. Yeah.
Okay, should we consider first exercises with FIFO and formula, plus formula and formula 2?
Uh, let's actually start from CPU. Yeah, because with Formula 1 and Formula 2, it's better to create a separate recording, because I think it will take like at least an hour and maybe more to discuss school risk 5. So let's actually just discuss school risk 5. So let's start from the beginning, from the baseline example. Yeah, can you make your font a little bit larger so it's like easier to read? Yeah, this is fine. Okay, so let's just go to 0554 and single cycle CPU. Yeah, maybe we can start from you introducing yourself. So you're like a teacher in Innopolis and taking so working together with me on this homework, and so we formulated problems in this homework, and now we are going to discuss CPU related problems. Yeah.
Yes,
Okay.
sure.
So just let's start. Yeah. Let me mute myself, and you can make a long speech.
So hello everyone. My name is Mike Kuskov, and I'm a teacher in Innopolis University. So together with Yuri, we developed a series of homeworks dedicated for system Verilog language, dedicated to different aspects. And today we're gonna consider the second part of the fifth homework dedicated to school risk CPU. And the first exercise in this fifth homework is just CPU baseline, which basically the same as basic school risk, just split it to several files. So as Yuri discussed previously, here we have a header file with all the constants for basic 9 operations, and other files for top level file for CPU itself, and dedicated file for decoder, instruction decoder, dedicated file for control unit, for ALU, and for register file. And I guess we can proceed with the exercises themselves. So here we can see just an example, just baseline CPU implementation. And the first exercise would be dedicated to the extension of this baseline with the multiplication instruction. So the idea of the task that we can analyze the baseline CPU and extend it with the support of multiplication instruction. So the program, like our school risk CPU, should be able to execute the following program of calculating factorial of the number. 1 second. Yeah. And here we have mul instruction, which is by default is not supported by school risk. So to add the support for this instruction, the first step would be to add constants, how we can decode this instruction according to risk manual. So should we go to risk manual and check how we can find this number, or we just assume that?
Yeah, let's show risk 5. Let's show risk 5 manual. Let's also define what factorial is, because there are many, especially students in different countries who know what factorial is, but they may not know the exact word. So this is just a multiplication: 1 multiply 2 multiply 3 multiply 4, and so on up to n. So we need to define such terms, just to make sure we define everything we talk about. Yeah. And if you can share the screen with the menu and just show description of multiplication instruction in the menu, this is useful.
Yes, sure.
Yeah.
So here we have a basic factorial program, and the idea of this program that we will use two registers, register A0 with the symbolic name A0 or numeric name X10. It's used as accumulator that accumulates the final result. And another register, T0, is used as temporary register to sequentially increase the number. So on each step of the algorithm, yeah, we will multiply our counter by the increasing number 2, 3, 4, and so on. And here we have, as our simple school risk CPU doesn't have unconditional branch instruction, here we use some trick with implemented instruction branch if equals z. So this branch will happen always. So it's kind of implementation of unconditional jump using implemented already existing conditional instruction. So the first step for the solution would be to define our multiplication instruction, or find the constants, how we can parse or like in general understand that we have received multiplication instruction. To do that, we will need to visit the RISC-V website and find the RISC-V standard, which is located in technical specifications section. So here we can find the volume 1 unprivileged specification for RISC-V. And could you see the document? Okay, I hope the document is visible. So here, the most important thing is like, yeah, here you could see the content, and we will be interested in M extension to the RISC-V architecture, which basically defines the multiplication and division operation. So, for example, we can read additional details about this multiplication and, for example, division operation. But the most important thing would be located, like, we'll be interested in how to decode this instruction. And the most interesting thing we'll be able to find in the instruction set listings. So here we'll be able to see the exact constants or the exact formatting, how multiplication instruction is encoded for RISC-V architecture. In listing, we could see the RV32 architecture, which is dedicated to 32-bit architecture. And here we need to find our multiplication instruction. So we can see that for RV32M extension, we have multiplication instruction that have three, like one opcode field, two functional fields, and another 15 bits of the instruction dedicated to the addresses of the registers with which we will work. So we will need to check the rightest common, which is opcode. We'll need to check the value like of this opcode, the value of funct3 field, and the value of funct7 field, because our multiplication instruction is basically R-type instruction. So this instruction works with registers, and we will need to add these particular comments or these particular constants that define multiplication. So we will, in our constant file, header file, we will say that RV opcode for multiplication is basically 0110011, as it's shown here, and as shown here. And like this opcode is similar for most arithmetic instructions and for all multiplication and division instructions. And after that, we'll need to define field funct3 and like F7. So for funct3 field, we'll need to specify 000 according to the standard, and the field like RISC-V funct7 field should be decoded as 7 bits, like 6 bits, 6 zeros, and then 1. Like once again, according to the table. After that, we'll already be able to decode our instruction. And the next step after adding such constants is to update our control unit. So we'll need to switch our decode unit. We'll need to switch to the decode unit itself. And here we will, like, we have the same format for decoding this instruction. This instruction. And the only thing, so here we don't need to update anything, as multiplication instruction fits to the regular R-type instruction. And decode unit we will need to update only if we introduce new type of the instruction, for example, to add the decoding of constants, additional decoding for constants. So as decoding is done usually, we'll need to visit the next step would be to visit the, I believe, control unit, with which we will already need to see what should be done when our processor receives the multiplication instruction. So the same, like there are two options how we can solve this exercise. We can either introduce new module, so we can either introduce a new dedicated module SR underscore MDU, multiplication division unit, which will do this particular multiplication or division instruction. And here, for simplicity, I have decided to integrate multiplication division instruction inside our arithmetic logic unit, which is actually not really correct way to do it, but still possible and very simple. So in control unit, we'll need to define what should be done when our processor receives the multiplication instruction. And the only change in this file would be to add the decoding of our multiplication codes and define that when our processor receives multiplication instruction, it will need to register or save the result of the operation. So the result of multiplication should be saved to the register. For that, we set rec write wire to 1. And later, we'll need to define or specify the explicit operation for our LU unit. And like in this implementation, we will specify that LU will need to perform multiplication. So once again, it's already several ways to solve the exercise. And in simple way, would integrate the multiplication inside our LU in a proper way or in the better way, we would define it separately in a separate module. And so here, for simplicity, we just give some constant or some opcode for internal LU operation. And after that, we can see that like the last step for this single cycle CPU for support combination multiplication would be to add this multiplication or like basically implement this multiplication the same way as all other arithmetical instructions are implemented. So based on our opcode, we have internal opcode we have received from control unit. Our LU will, like in this case statement, will just perform the multiplication operation combinationally. So such solution will introduce greater delay compared to more like simpler plus or bitwise operations. But for simplicity, this is fine. And all the other modules, so all the other modules will stay unchanged. And we can check that when we receive multiplication instruction, it will be decoded as any R-type instruction, which is already implemented. It will be control unit will recognize this instruction and will specify the special multiplication opcode. It will transfer this operation code for ALU. ALU will perform the instruction, the multiplication itself, and this result of ALU here, it will be saved to our register file. So as we remember in control unit, we have specified that we activate, like enable register right, and then we save the result of multiplication. So that's basically it for simple combinational multiplication. And further, we can consider the multiplication with latency, or we can leave the multiplication with latency for should we consider B instruction first or go with multiplication with latency? Okay, so the next task is to implement multiplication unit or multiplication operation with some latency, which overall can be arbitrary, like from two clock cycles up to n clock cycles. But no, yeah, this is the main idea. And here we will need to do all the same steps as with combinational multiplication, combinatorial multiplication. So the program that our CPU will need to execute will stay the same. Our CPU will need to calculate the factorial, and the same way we'll need to define constants. So we'll need to introduce we'll need to get the opcode operation from our discrete standard. We'll need to get F3 field for multiplication and F7 field for multiplication. The difference with this task would be the following. So as task requires to implement multiplication with latency, it means the result of multiplication will be ready after some time, like after some count of clock cycles, for example, 2 clock cycles. And in this setup, it's already easier or more like better to implement multiplication in a separate file. So after adding the multiplication to our constants, we can check let's check the interface for our multiplication unit, which is already separate unit in our school rescue. So here we need to here you will be provided with this interface, or you'll need to create this file from scratch. It will be decided. But the idea of the unit that it will have the same clock cycle as the whole CPU. It will have reset signal, and it will have two input signals. Like one of them is input valid, which states that the current values of A and B are correct, and the operation of multiplication should begin. And after that, we have basically two 32-bit values, A and B, which we should multiply. The output of this model is either flag or valid, which says that multiplication is finished, and further steps of our CPU can take the result of our multiplication model. So this flag is not used in single cycle implementation, but this flag could be useful in a pipelined version of school rescue. Like also we have 32-bit result, and the last flag is flag busy, which is set when our multiplication division unit starts to perform basically multiplication operation. And the idea of this flag is to stop the whole processor from stop or freeze the whole processor on the current instruction and wait until the multiplication division unit finishes its work. So let's see how this signal is used, first of all. So let's see how we can stop our single cycle CPU for a couple of cycles, and then we will check internals of our multiplication division unit. So the idea here generally the same. Generally the same compared with combinational multiplication. So we will need to add a constant. After that, we will need there will be no need to change the decode model. So we decode this instruction the same way as all other instructions because it's R-type. And we will need to modify control unit. Here we will need to introduce two things. One of the things we will need to introduce is control signal for multiplication division unit. for now, it's for now it's basically signals or flags. Like this is the flag that multiplication unit should start the multiplication operation, and another second flag is right destination, or like basically the second wire we will need to add to our solution that will send a signal to the processor that the result of multiplication division unit should be written or should be saved to the register. So as well, like as with ALU model, we have ALU control signal and ALU source signal or destination source register source signal, result register source signal. The same thing we have with multiplication division. So here we will need to add some combinational logic to fire the signals, and the same way as with combinatorial implementation, we'll say that when we see multiplication operation, we will save the result of multiplication to the register. We'll need to save basically the result of multiplication unit to the register, not the ALU or immediate from the instruction itself. And here we specify that we are interested in performing multiplication operation, basically. So for future, this could be this step could be enhanced with the division operation or, for example, a reminder operation. And after that, so after we decode our instruction, we can come back to the core SR underscore CPU model. And here we will need to introduce two signals that will, like one of the signals will stop the processor for some amount of clock cycles, or another way, this busy signal, for example, will create a stall in the processor to wait until the multiplication division unit finishes its operation. And we will need one wire to define the source from which we should save the value to the register. So regarding this file, we can see, like, after that, all code stays the same. And here we have two important steps. So one of the steps is this source file, source control signal for the source of write register. So here we can see that, here we can see that if our control signal is set, we will save to our register. We will write to our register result of multiplication division unit. So here we can see that we create additional wire to connect a result of MDU model with the wire connected to the write register write of our CPU. And another thing that we'll need to connect the busy signal. So when our MDU model is busy and like it would like to stop the CPU for a couple of cycles, we will see that here we will introduce, like after ILU, we'll introduce our MDU model. We'll connect the busy signal, and we can see that when our MDU model performs the operation, it will set the busy signal, and it means that our program counter register should not be updated. So in other words, we'll need to upgrade our program counter to enable register. And we will need to specify that our program counter should be updated only if our processor is not stopped, or like there is no like waiting for the result of multiplication. So this is one of the steps we will need to perform to respect the busy signal. And another step would be to add like this enable add this signal to the creation of enable signal for writing inside register file. So here, basically, we'll need to specify that there is no need, or our register file should not be updated if MDU model is busy. So here we use negotiation, not operator, to convert the value of our busy, and like otherwise we can call it as working. Okay. And the last thing would be to see how our MDU model is implemented internally. So here we can see that we do not utilize the valid operation, like output valid flag. And this is because in this very top solution, we do not implement pipelining. And in this solution, we just do simple stall, or we just stop the whole processor for like several clock cycles. In another solution, we would ignore the busy signal and we would forward the output value to the next stage of the pipeline in our processor. And the last thing in this simple implementation is how our multiplication division unit is implemented, and how our output valid signals and busy signals are combined created. So we as we will work, we could work with arbitrary number, arbitrary latency. So we will introduce parameter that will parameterize our multiplication block. By default, it will use 2 clock cycles as latency, but potentially it could be increased up to 4 cycles or 32 cycles or any arbitrary number. And here we will need to basically do 2 things. One of the things would be to define the valid shift register, which will forward, or which will shift the input valid signals, and which could be used in pipelined version of the model. And also we'll need to define, so this is valid shift register for the control flow, and here at the end of the model we'll need to define shift register for the data. And we can see, for example, that our data is pushed to the shift register basically every time as as we receive input operation, input weight. So when we want to perform the multiplication, or when we want to basically perform the multiplication, we will push the value, the result of our operation, and we'll kind of use some trick or handcrafted way to delay the result for 2 clock cycles. And as we are delaying the result for 2 clock cycles, we will also need to do the same for delaying the control signal, basically shifted for 2 clock cycles. So here we create shift register for 2 bits, and then we have additional wires. One of the wires, one of the things we will need to do is to create an empty signal that basically says that our MDU unit is empty and it doesn't have any multiplication results flowing in data path. So here we check that we have all, if we have any ones in our valid register, and then invert the value.
Yes, Mike. Let me give you some important note. This this module is effectively a model of MDU. This is not how usually RTL for MDU is implemented, because here, instead of doing part of combinational pass of a multiplication in one clock cycle and part of combinational pass in another clock cycle, we are essentially doing like everything in the first clock cycle, and then just delay the result. So this is not something we would do in RTL, and we just do it here to model the behavior we want to show during the simulation. So maybe we can even like call this module as MDU model, and then create a define where we do if def, and like if def use model, or like if def use use multiplication where combinational logic is spread in 2 clock cycles. So this like one thing. Second thing, if this is a model, in this case, for this null result, we can put, if not push, we need to assign access. So this is like second thing. And third thing, oh yeah, there is a such thing as automatic retiming. Is some advanced synthesis tools, including tools from Synopsys and Cadence. They actually allow to write just the code Mike wrote with a multiplication operation in the first clock cycle and several clock cycles of delay. And then such tools automatically do retiming. And by retiming, I mean moving combinational logic to different stages of pipeline, and can actually implement pipeline multiplication unit using this technique. However, from another side, I can tell you that some companies don't like automatic retiming, and in like at least one case, when we got in one company, when we licensed IP from another company which had automatic retiming module, one of tasks was to convert it into modules with explicit combinational logic in each pipeline stage. So we can put some notes about it, and maybe make even some slides about automatic retiming versus manual pipeline stage for such heavy mathematical operations. Yeah. Okay. So let's continue.
So yeah, as Yuri mentioned, this is not this is not the solution. It's just a model of, I mean, one of the options how to implement this multiplication with latency, and ideally it could be implemented. So this operation that of multiplication that is performed basically on the first cycle, it could be indeed implemented as multi-cycle operation. So the idea here is just to forward, create the, get the result in first cycle, and then delay it for some number of given clock cycles. And the same way to do with the control signal, of busy, or basically the using shift register value. And important note here, that solutions could be different. This is not the only and the only correct solution. And here we assume all all variants, or a lot of variance or variability. And that's basically why we provide an interface and allow students, for example, to implement to implement a complex solution where they could pipeline the whole CPU, and already, in this case, signal busy will not be used. And in the most advanced way, signal busy also could be used to, in combination with, for example, forwarding of multiplication result to the next multiplication operation if they will have dependency in the result and the argument. So here we just present the model, and the solutions could vary in complexity and other parameters. It would be also good to show that, okay. So I guess we can move forward, and if there will be any questions, we can discuss them. So this was the second exercise. That is basically to implement multiplication with latency. And the third exercise for school RISC-V CPU is to implement branching or jumping instruction. In other words, to implement the unconditional jump. And the first step students will need to see in this exercise is program, which will be used for, like, in a benchmark to see how the solution was implemented. So here we have a program in RISC-V assembly language that calculates the Fibonacci numbers. I guess, yeah. Should we explain what is Fibonacci numbers, or we'll just assume that our listeners know the concept? Okay, no. So anyway,
You actually
basically,
explained already what is this
mm,
number before.
okay.
So this moment we know this already. Yeah.
Okay, so the only difference, this is basically the same program as, for example, in
Oh, wait.
no,
I'm sorry. You explained the factorial, but
yeah.
just for the sake of completeness, let's explain what Fibonacci is as well, because in like some countries, like even like those numbers included into program of like high school, and in some countries they don't. So we need to define what it is.
So basically, I guess the simplest way would be just to show the sequence. And here we could see the sequence of Fibonacci numbers. We could see that this sequence starts with the first Fibonacci number, which is 1, then goes the second Fibonacci number, which is also 1, and all the following terms of the sequence should follow this rule. So we can say that the first Fibonacci number should be the sum of two previous numbers, or in other words, the sum of first and second Fibonacci number. And the same way, for example, the 10th Fibonacci number is the sum of 8th and 9th Fibonacci number. And in this way, we can, so this formula is iterative, and applying this formula to first two basic Fibonacci numbers, we can get any Fibonacci term like up to infinity. So for example, here we have 15 Fibonacci number, which is sum of two previous numbers, 233 and 377. And in our exercise, we have the program that calculates the sequence of Fibonacci numbers. So as we can see, we start with 0. So the same way as with factorial, here we use the accumulator register A1 to accumulate like result of our operation, and then we use temporary register. And at the beginning of the program, we store values 0 and 1 to our registers. After that, we can see that we use third additional temporary register T1, to which we calculate the sum of our two registers, or like of our two Fibonacci numbers. And as we can see, after that, so we calculate the third Fibonacci number, for example, save it in the register T1, and after that, we update our basic registers. So we save T0, the second Fibonacci number, like in the beginning of the problem, it will be 1. So we save it to A0, and the result of our sum, we save it to T0. And after that, we can see that initially our program, we're using so-called like almost unconditional jump. So here we were using conditional jump on branch if equals 0, which basically compared 0 with 0 register, and we're always jumping to our label loop. But in this particular exercise, we'll be able to use unconditional jump through the branch instruction. And here we will need to implement this branching instruction to loop, to jump on our label loop, without any checking any conditions. And the first step to do so would be to check the manual and see how unconditional branch or unconditional jump instruction is encoded in RISC-V standard. So the first thing we will need to do, the same as with multiplication operation, we'll need to add the constants based on our standard. So we can come back to the standard. Here in the contents of the standard, we can, for example, find the, one second. So here we can find all the additional information we might be interested in, like in regard of jumps. One of the things is, for example, how jump instruction is encoded. So in RISC-V architecture, we have a separate instruction type, J-type, for jumps. So we have B-type instructions for branch instructions or conditional jumps. And we have J-type instruction for jump instruction to perform the jumps. And as we see that our J-type instruction, like if we compare the structure or the fields of our instruction, it is different from B-type instruction and from R-type instruction. And we can see that in our jump, unconditional jump instruction, we'll have the most significant, how much? 31, like around 21 most significant bit, or like 20 or 21 most significant bit dedicated to the offset to which we'll perform the jump. So RISC-V architecture is able, like, consciously follow, like here in the standard, you can find the notes, for example, from authors from of the standard, and the authors mention that they consciously implement only program counter relative or PC relative jumps. So with this 21-bit, we'll be able to perform the jump in a region around 4 kilobytes, if I remember correctly, relative to our current instruction number, like relative to our current instruction we are executing. And the next thing we can see, according to the standard, that jump type instruction compared to the branching instruction have also special field dedicated to the address or to the number of result register. So as the result of the jump operation, we will need to save some value to the to the register in our register file. Here in the standard, we can, we can see the description of our J-type immediate values, and a bit lower we can see, we can see control transfer instructions which is basically J-type instruction or JAL instruction. So J, like instruction J in RISC-V architecture is pseudo instruction, which is not really implemented in like hardware, and this pseudo instruction unrolls or like assembled as just JAL instruction with saving result to 0 register. So this is the details. It's better to show them on RARS simulator. So it's better to see how this J instruction is, like how this J, how this branching instruction or J jumping instruction We have some noise in the background. Sorry. Mikhail? Yeah, thank you. So,
why is the unconditional jump instruction coded as a B? Why shouldn't it be just something like JMP?
Ideally, according to this, this is caveat that we with Yuri spotted just right now. And the problem is that according to the RISC-V standard, there is no B-type instruction. So like according to the standard, strictly speaking, there is no such instruction. But as we use RARS simulator heavily for our homework, and as we check all these programs in RARS simulator, for like due to historical reasons and due to historical reasons, for some reason, RARS simulator works with these B unconditional jumps, and basically I can even show, yeah, let me try to show it on RARS.
Wait a second. Is B supported by GCC toolchain? Like, is it like a Fisher pseudo instruction? Because if
sure,
it's not, then we should change it to jump.
Yeah,
simply. Yeah.
So most probably this is the legacy of RARS, and we will change it just to J instruction, jump instruction.
Yeah, let's actually check whether it's a real pseudo instruction or whether it's a legacy of RARS. It's a, yeah. I didn't thought about it. B was a pseudo instruction in MIPS, like I believe it was like, but it was a shortcut for B equals 0, but it may not be the same for RISC-V.
So in RISC-V standard document, we have explanation that plain unconditional jumps, assembler pseudo instruction G, is encoded as JAL instruction with destination register X0, so 0 register. And I have not seen any mention of B instruction in RISC-V standard. So this is most probably legacy of RARS.
But this is no, but probably RISC-V standard does not even list a pseudo instruction. Does it list the LI pseudo instruction? This is just a feature of assembler. So we need to check whether GCC toolchain has this as a pseudo instruction. Because standard is simply not applicable. Standard does not list even LI, because this is instruction standard. It's not standard for assembler conventions. So we just need to Google for list of RISC-V pseudo instructions.
Well, actually, if I remember correctly, there's a list of pseudo instructions in a RISC-V document in the end.
Let's check.
In this document, or
yeah,
like another document?
After real instructions, there should be a list of pseudo instructions as well, if I remember correctly.
Okay, let's see.
That's actually a good question.
There is a RISC-V assembler reference, but assembler reference is not instruction. So assembler instruction set reference.
In RISC-V assembly handbook, we have ABI names for the registers, and lower we have list of pseudo instructions. And here, like, we have a definition of load store instructions, load address instructions, and load
this
immediate,
is like probably different files. So let's just find appropriate file which lists assembly pseudo instructions, because I can see it in GitHub, but I don't see it in this document. So let's just find the official list of pseudo instructions.
Isn't that it right there, Yuri? It says jump offset. That's the pseudo instruction.
Oh yeah,
Yeah,
this has
I
a
believe
pseudo.
this is
Okay,
it.
okay, this fine, this fine. Okay, so let's see. Does it list a lie pseudo instruction? Let's go up. No. Yes. Okay, okay, okay. This is fine. This is fine. This does list a pseudo instruction in this document. Yeah. Okay, this is fine. So you found it. So B is not here, right?
Yeah, here we have only conditional B. Like, I guess.
Okay. In this case, we need to change. In this case, we need to change this task, and we need to change it to jump instruction, and have just J offset instead of B. Yeah. So B is just some like artifact of RAR's simulator. Okay.
Yeah, and so here we would need to use J instruction, which is pseudo instruction for JAL with zero register x0, and next we'll need to see how to basically implement this JAL instruction. So this is interesting exercise that initially we will need to we'll be interested in implementing J pseudo instruction, but to implement this pseudo instruction, we'll basically need to implement JAL instruction, which saves the some result to the register file. And with such implementation, we'll get for free JAL pseudo instruction or JAL already real instruction. Yeah. Wait. So there is two JAL instructions. What should okay, yeah. So implementing J pseudo instruction, we will need to implement fully the JAL instruction that takes two arguments, destination register and offset. And for free, we'll get also implementation of one argument JAL instruction, which by convention links or saves the address to X1 register. And this X1 register is return address register, if I remember correctly. Second, let's come back to assembler's handbook. Yeah, X1 register is return address register.
We should mention here that this is calling convention, so which is here ABI convention. So this is convention to make sure that we can call functions in like a C code and between different programming languages in a predictable way. Yeah. So from the point of view of CPU, those registers like JAL X1, JAL X2, JAL X3, they could be treated the same. Or CPU may have some special optimizations for X1 only. Like some CPUs, they have a special call like return address predictors, which use the fact that CPU uses certain register to store return address. Yeah. Okay.
And yeah, and actually in the standard, we have comments from the authors of the standard just describing this case that why, first of all, here is the comment why it was decided to use branch instructions together with compare instructions and why authors decided to get rid of state registers, if I remember, status registers, if I remember correctly. And there is also a comment regarding the branching, the branching prediction and explanation, why it's better to follow the common convention and to store the return address to X1 register. So I don't remember where it's located exactly, but I have seen in the standard this explanation why such design decisions were chosen. Okay, so yeah, here, for example, we have explanation like how PC relative jumps are done and how like far jumps are implemented in like could be implemented in RISC-V. So we'll need to, yeah, let's come back to the exercise. And like as we remember, to implement pseudo type J instruction, we'll need to implement like full jump instruction to the arbitrary offset of 21 bit. And here we, for example, will see the note that to perform long range jump, assembler will need to convert the long range address to, like usually we'll convert the long range jump instruction to combination of two instructions, which is load upper immediate and then jump. So coming back to the task itself, we'll need to first of all check the format of our JType instruction, and then we could come back to the instruction set listings just to see and indeed check how our JAL instruction should be decoded. So in this exercise, the first step for the solution will be already to upgrade our decode module and extend it with JType immediate. So the first step would be to add this immediate to the module, and basically the decoding of the opcode and decoding of the destination register is the same. So like as we see here, yeah, okay. So first of all, we will need to add this opcode constant to our constants file, to our header file. So yeah, the first step would be to update our constant file here, and JAL and JAL-R instructions, they use only opcode field, so they do not use as some different instructions, they do not use F3 field, they do not use F7 field. They just basically encode it with purely opcode field. And for example, if we want to add JAL instruction, we will need to add it to the opcode JAL instruction, and then for future we will use, yeah, like we will see how, like what value we will use in control unit. Okay, so the first step would be just to check the opcode of JAL instruction and add it to our CPU. The next step, as I already mentioned, would be to upgrade our decode model and to add the decoding of JType immediate value, or the address where we will perform our job. For that, we will need to come back in the standard. We will need to come back to control transfer instructions, and we will need to find the following diagram, based on which we will understand the structure or the meaning of bits in our instruction. So we will see that the first the first 7 least significance bit are dedicated to the opcode, which is already implemented here. Then we will need to check that next 4 least bits from 7 to 11 dedicated to the destination register, which is decoded here correctly. And then the last thing we'll need to do is to perform the decoding of our jump JType immediate value. So we can see that upper or most significant, 21 most significant bit is dedicated to the encoding of our jump immediate value. And later we'll need to find how this jump immediate value, where can we find it? I guess in the listing. So let's come back to the listing. And here we can see the encoding of the instructions. yeah, this is encoding of the instruction, but we need to find the encoding of immediate values. Probably it's like could be here in transfer, or I saw it. In the beginning of the standard, yeah, here in the beginning of the standard, we can see the encoding of different type of immediates. So, for example, when we want to decode immediate type instruction, so I type instruction that contains some immediate value, we could see how this immediate value or constant value can be recreated, reassembled from the instruction. So we'll need to use most significant 31st instruction bit as the sign extent value of our immediate value. And here for jump instruction, we could see that we have the least significant bit always equal to 0, because basically jump immediate value encodes the address in memory when, or like offset the memory address where we want to perform our jump. And in RISC-V architecture, memory is usually word addressable, which is 4-byte addressable, but under some conditions, it's also half word addressable or 2-byte addressable. And it means that we cannot address our instruction memory on byte basis, and that's why the least bit is always equal to 0. So we can address only with 2-byte difference. And after that, we can just check how to decode this value. And here, basically, we implement this decoder. So we assign the 0 bit of the immediate value as always 0. Then we decode the inner part of the immediate value. And then we duplicate the most significant 31st instruction bit. We duplicate it 12 times just to fill the most significant bits of our immediate value address, offset address, or offset more precisely. And after that, we can just return this immediate back from our model. And after that, what else? So we have implemented the constant. We have provided the constant how to decode JAL instruction or JTAP instruction. We have modified our decoder to retrieve immediate value from the instruction. And the next step would be to perform the setup, or perform the proper setup of control flags. And for that, first of all, the same as with the same, I believe, as with branching instructions. Here we'll, the same as with branching instructions, we'll need to add some special. So this is one of the variations. And in this variant of the solution, I have decided to add special jump flag, which will be respected by other parts of CPU, and which will be used to perform unconditional jump. So here we can see, for example, how branching is handled, and we can see that there are two options how to implement this homework. Either we can increase dimensionality or increase width of PC source wire. So we can say that PC source wire will be encoded using already 2 bits. And in future, we could use this PC source. So in future, as we could see, we use this PC source value here, program counter SRC value. Yeah, we use it here. So we use it here in basic CPU baseline, we were using this PC source signal to determine whether we should perform the branch or not. So whether we have received the branching instructions and we have fulfilled the condition, so we can update the address of our next instruction. And there are two options how we can implement our current task 10. So either we can increase the dimensionality of PC source just to include this third option, or we can more kind of high-key way, I would say, add additional flag jump that basically serves the same purpose. And like we will come back to it a bit later, but we will need to see how we can handle this jump flag. So we will just set this jump flag to 1 when we have decoded the jump instruction and when we will basically would like to perform the conditional jump. And we will need to add default value for jump signal. And then the last part to do would be to set the proper control signals depending on our jump. So basically, I guess here, do we need, so here we will, based on our opcode value of JIL jump and link instruction or jump instruction, we will use that we care like here, as we should write our case for all 3 opcode fields. So we should respect the funct7 field, funct3 field, and the opcode itself. Here we'll use a special constant like rvf3 any and rvf7 any, just to say that we don't care, or like this case statement should ignore the f3 and f7 fields, because when we have JAL opcode, these fields will contain the like bits of the offset, and we like do not actually care what value is stored there. So we will use any value that is stored there, and we will match the case of our opcode. And when we have jump, like when we have recognized our opcode from the instruction, we will say that we will update the value in our register file. So we will send the control signal to update some register. We will talk a bit later what exact register we would like to update. And after that, we set our jump control signal also to 1. Here, as an alternative, we could we could set the same as with all branch instructions. We could set, for example, branch to 1, and then like as we here set branch to 1, we could set here jump to 1, and then create just proper program counter source value, which will be 2-bit, and like here would extend this statement and end handling for unconditional jumps. In the current solution, I've decided to straightforwardly input this signal, and let's see how this signal is handled by CPU. So the control, like SR control in the last the last model will need to change. And all further improvements will be dedicated to CPU directly. So we'll need to introduce this jump wire in our CPU. And then, we'll need to introduce jump wire. To wire it up with control unit, we'll need to introduce immediate wire to wire it up with the decode unit. And after that, we'll need to introduce 2 new wires to properly calculate the value or properly calculate the address where we should perform our jump. So with branch instructions, we were calculating it as current program counter value plus B type immediate. With jump, we will do basically the same, but with the J type immediate. And after that, we'll need to slightly modify code for updating program counter. So here when we, let's say, create or like define the value for the next instruction, we'll need to add this multiplexer, I would say, that will perform the jump or will store the address of future instruction based on our control flag. So if we have control flag set to 1, on the next clock cycle, we will already fetch instruction like based on the provided offset. And here we will not like there will be no changes to the program counter register itself. There will be no changes to the fetching of the data. We'll need to add this new port, output port for J-type immediate value, and the last important thing is that according to the RISC-V standard, so if we come back to control type instructions, according to RISC-V standard, we will see that our JAL instruction should store the address of the following jump, should store the address of the instruction following the jump. So basically should store the PC +4 or PC next value to our destination register. And that's basically what we do here. So here we define what value should be stored to destination register. And here, we either store the result of our arithmetical operations from ALU or directly from the instruction itself, or if we perform the jump, we will store the address of the next instruction. And for example, for J-type pseudo instruction, we will store it to 0 register, which basically does nothing. So, and the last thing for the solution would be actually to update the output port for control model, which just wires the jump wire, like links the jump wire with. So that's basically it. So to add the jump instruction, let's briefly sum up that to add jump instruction, we'll need to update constant and add opcode of our operation for performing jump. We'll need to update decode model to properly decode an offset of the address to which we will jump. The next thing would be to update control model either by increasing the dimensionality of PC source register. So here we'll already have 3 variations how to update our program counter. So either next instruction PC +4 or branch instruction like PC plus branch offset, or jump instruction PC plus jump offset. And the last thing would be to update control model. And the last thing would be to update just wires and wire everything in our main CPU. So like if we have some questions, we can discuss. If not, we can go to the next exercise dedicated to fetch with latency. Okay, so for fetch with latency exercise, the idea of the exercise is kind of similar to multiplication with latency, but here in fetch with latency, we will work with like instruction fetch model that has some like latency on given number of clock cycles. The first thing, let's check the example program, and the program is same as basically baseline. So the program here has no difference with basic program in CPU baseline example. It just calculates Fibonacci numbers using the basic 9 instructions provided by baseline CPU. If you are very interested, here you could copy, for example, like rewrite this instruction with J-type instruction or uncomment the factorial number and then copy all your solutions from previous exercises to have more extended CPU or more enhanced CPU. But like basically it's not required by the task. And the idea of the task that we have slightly modified instruction ROM. So in in this exercise, we'll have a new interface for instruction ROM memory, and this interface will have additional flag whether the current instruction is valid. So the idea of the exercise that this instruction ROM memory gets the address of the instruction in one cycle and provides the address or instruction data in the next clock cycle. And to do that, we'll need to add handling for our valid flag. And basically the idea would be the following. So if the idea would be the following, first of all, we will fetch the instruction here from our, so when the instruction comes, like when we receive the instruction address, we'll fetch it from our ROM memory and save to output register, but we will do it in the next clock cycle. So the next thing we would like to do is also to save the address of our instruction so that our the data of the instruction we fetch and the address of the instruction we fetch are similar. And here we could use this registered value of address to probably to define the validity flag for our data fetch. So
Yes,
when
Mike, you probably said this, but I now got interrupted. So this ROM is again, this is a effectively model of ROM. So we just like imitate ROM which may have the same property implemented using different physical technology. Yeah, this is what we frequently do in like ASIC design. We are using different model for simulation and synthesis, and a different memory model for like FPGA prototyping. So we are here effectively creating FPGA, creating a synthesizable FPGA prototype, and at the same time a simulation model of a certain memory entity which in ASIC can be implemented as ASIC memory block or so on. But for our purposes, this is enough because this module behaves identically from the timing perspective as a physical like a SRAM or ROM embedded into ASIC.
Yeah, and the basic idea of this model is just to return return the data. So basically, that return requested instruction on the next clock cycle. So in the first clock cycle, we request the instruction by setting up the address. In the next clock cycle, we receive instruction with the proper, with the correct read data valid signal setup. And so for this model of ROM, we'll need to modify our CPU to properly wait while wait for the valid flag from ROM and do not do anything if the current instruction which arrives to our CPU is not valid. So here, I guess we'll need also to see how our CPU is linked or wired with our ROM memory. And here we can see that we have additional instruction memory data valid flag, which just directly passes, which just directly connects the output port of our valid flag of the RAM with the input port of instruction memory valid input port. Yeah. So here we can see that the address is passed to our CPU directly with validity flag. And for the exercise, we'll need to implement proper handling. So in this exercise, there will be no need to change constants because we will be working with CPU itself. Like there is no new operations introduced. So we'll need not like there is no need to change header file. There is no need to change decode stage, the decode model, control model, or ALU model. And the only thing we'll need to change our main CPU to respect this validity flag of instruction memory data. And basically the change here is quite straightforward. So if our validity flag is not set, so if the currently fetched instruction is not valid, it means that our processor should stall or should not do anything. And as we saw with multiplication with latency exercise, we can implement this kind of full processor stall just by forwarding this instruction memory data valid flag to two registers. So first of all, we'll need to pass it to our, first of all, we'll need to upgrade program counter register, make it program counter just register with enable flag, and we'll need to pass this validity flag as an enable to our program counter. So if current instruction is not valid, we will not save the next address of the next instruction, and our processor will stall on the current instruction. So this is the first change, and the second change is dedicated to handling enable flag with register write. So when we see that the current instruction is not valid, we should not perform any write to our register file. And in other words, we can see that we should perform write to our register file when we have a control flag set on and we have the valid instruction. And I believe these two small changes is all what we need to do. Let me check the register file itself. Yeah, so we provide in this exercise, we provide you with already existing and implemented by us register with enable and reset. And the only thing we expect from students is the proper handling of valid signal, instruction memory data validity signal. So I guess there will be, so if you have some questions, we can consider that. But overall, we can move to the last exercise, which is already a quite interesting exercise, where we have three CPUs which share the same instruction memory. So in this exercise, first of all, let's check our RISC-V assembly program. And then we can see that in this exercise, we already have two programs in the similar file. But the interesting idea that if we try to execute this program on the single core CPU or single processor CPU, will be infinitely, our processor will infinitely execute the Fibonacci number and will not ever go to the factorial. And the interesting idea of this exercise that we will provide here, we provide two different programs that together compute the factorial of the number, the Fibonacci numbers, and the factorial of the number, and they will use different CPUs. So in this exercise, we use different CPUs to simultaneously compute both of these programs. And let's see what we have here. The first, we can inspect the ROM memory, and basically the ROM memory is implemented the same way as in baseline and as in all other CPUs except for the previous task. We have combinational single cycle access like to the memory. So the same way, like the same at the same time instant we have set the address, like in the same clock cycle, we will receive this address because it's there's no any latency. The next thing we'll need to check is how our three cores are wired together. So idea of this exercise, the idea of this exercise is that we have a special new file that is called CPU cluster, that is basically defines the amount of CPUs we have in this file, and also the personal kind, let's say, unofficially personal signals for each CPU. So as we can see, here we'll have 3 CPUs, and we'll have 3 32-bit wires to provide reset for each CPU, also to provide the and debug interfaces for register address and register data. So the interesting idea of this exercise that we will extend our CPU, and we will also be able to provide the reset address or reset program counter from which the CPU should start the execution. So in this exercise, we'll be able to start the processor from some given program counter, and that processor should use after the reset. Then later here, we can see that our solution. So here in the solution, you'll basically need to create 3 CPUs, connect all of them together, and use given round robin arbiter to properly select or grant access to the single shared instruction memory to all 3 CPUs. So the idea of the exercise that here we can generate like given count of processors. Like in this particular example, we will generate 3 CPUs, and after that we will connect all the wires. So we'll connect the reset wire for program counter, like which program counter value we should with which program counter value our processor should start after the reset. And also we'll connect the wire with address of the instruction that current processor requests, and connect with data of instruction basically that processor have requested. So we have 3 CPUs, and like each CPU will request some address, and using the arbiter, we'll select which particular CPU will need to provide an instruction. So here later, we have some code dedicated to the request. So we will have, at most, we could have here 8 different CPUs, but currently we'll work with only 3 of them. Right, yeah. So we'll set that all 3 CPUs would like to get would like to send requests to our instruction ROM memory, and after that we will provide grant only like this grant wire only for 1 out of 3 CPUs. So idea here that we can request, so we can based on the grant bit, we can request from the memory only the address of the instruction asked by CPU to which we would like to grant access in this particular clock cycle. So it would be easier to consider it, like it would be easier to see the expected work of this model on the timing diagram. But overall, the idea that in each clock cycle, we will grant access to different CPUs, like out of our 3 CPUs. And in each clock cycle, we will request different instructions based on the address of the CPU to which we provide grant in this clock cycle. So for example, we could provide address to the first CPU and then get the address this first CPU would like to fetch. Then fetch this, like basically combine all the possible addresses, fetch the address, provide the instruction based on this address, and later this instruction will be forwarded to particular CPU interested in this instruction. And here the last interesting step, that based on our grant, we can define the data validity wire. So here, as we have 3 CPUs, we will define 3-bit with data validity wire. And if, for example, our arbiter decides to grant access for the first CPU, we will, like here, we'll have here sequence of 0, 0, 1, which is basically the grant for the first CPU. And this first wire will be connected to the instruction validity data valid flag of the CPU, which we already saw in previous exercise. And basically what it means is that when like our arbiter will provide access only to 1 CPU out of 3, and in other words, from CPU perspective, the CPU here will have data validity flag set to 1 only like at 1 cycle out of 3. So this, like the processor will see the grant from the arbiter, will perform the instruction, will write data to the register like file, and then will stall or like will be deactivated or will be like waiting to execute the next instruction for 2 more cycles. And this way we'll have kind of model of the system with 3 processors, and like each processor or each CPU will work on its own instruction in its own dedicated clock cycle. And here, I guess the last thing, so for solution, in the CPU file itself, there is no need to change anything, and the most complexity or like the most changes should be done in the CPU cluster file, because here there will be no code at all. So here you would see only the definition of the cluster, and basically that's all. And you'll need to initiate the arbiter and connect the data, like instruction data wires, and initiate the RAM memory, and connect all the wires, connect the arbiter with instruction memory and with 3 or any other amount of CPUs. And the last thing, interesting thing, is just to check the test bench. This is not part of the solution, but for curiosity, we can check the test bench. And for example, first thing, we can see what is expected from our CPU to like what is expected as a result of the work of our CPU. And also we can check, for example, what values are provided to our program counters after the reset. So here we could see that, yeah, like when we send a reset signal to our cluster, we will see that 2 our CPUs, or vice versa, that 1 of our CPUs will perform the factorial operation because it will receive the address of factorial instruction, like the it will receive the address of the instruction that will calculate the first instruction of calculating the factorial. And we can see that 2 other CPUs will receive the address of Fibonacci number. And basically what we say is that on reset, one CPU should start with factorial, set its program counter to the factorial, and another 2 CPUs should set their program counters to the address of first instruction of Fibonacci program. And the later test bench just checks the work of the solution of the student. So you could check the diagram or run the simulation to verify the correctness of the solution. Okay, so if you have some questions, we can consider some questions for now, but overall, this is everything. Yeah.
Let me actually add one important note about this exercise with 3 CPUs. One, we actually plan a number of exercises with a multiple CPU cores. And the next step after doing 3 CPU cores sharing the same memory for fetching, the next step is to make them to share multi-bank memory. Because in this case, there is a limited resource of 1 memory port. In principle, we can make memory with 3 ports, but in a real life, in ASIC, you usually have like a pseudo dual port memory, which means that 1 port for read and 1 port for write. And if you have multiple readers, you need to share port with arbitrary, which slows down all the CPUs. So they start to work like 3 times slower than necessary. However, if you introduce so-called memory banks, which are effectively multiple memories sharing the same address space, different parts of address space, then if 1 core mostly accesses only 1 bank of memory, and if you don't have bank conflict, then all 3 CPU cores can work as if each of them has its own private memory. And only sometimes when they use memory banks of each other, in this case, yeah. So yes, so this is a good, this is a good diagram. Let me make sure this diagram is correct. Is this correct? Yeah, it's a kind of, yeah, it's a kind of like this. So in this case, unless you have bank conflict, so you don't have a performance degradation. So the next step would be to create such a multi-bank memory, but in this case, ROM may not be the most convincing example. It would be nice to give a student, like I said, maybe task for a course project, to implement a memory controller which uses a real memory chip, like on FPGA board, and make him to do a presentation and show a demo how multi-bank memory helps the performance. Like also, if we continue with multiple cores, we can even make cache coherency protocols, but we need to do more complicated cores for it, and maybe we can use MiRISC-V core in order to implement such example. Yeah, so this is kind of addition to this exercise with multiple cores sharing the same memory. We may also consider creating an example where multiple cores exchange messages with each other using FIFOs, but this is kind of a separate topic, so we'll present it later. Yeah. So if there are no questions, let's actually go back to CPU multiplication with latency. So I want to show a solution which was created by one a graduate student who is now actually once I saw his solution, actually forwarded it to hiring manager in the Samsung. So because this is like one of those students who can quickly produce good good complete answers to the exercise. So he not just simply stalled a CPU, but he actually created a pipeline with forwarding that allow to maximize the performance when you have a sequence of ALU and multiplication operations. So while you're doing multiplication operation, you can continue to do ALU operation. So let's look to his example. So he like agreed to share it for like open source project. Yeah, and this is something I want Mike Kuskov to implement as well. And we can make some maybe a little bit nicer version of it. But let me get his solution. Just a second. So this is Wagner. Okay. So let's see. Yeah, so this is his version. So if you go to CPU, you can see that he created multiple copies of read and write, read signals and signals like immediate. So he created a pipeline by creating multiple copies of a signal, and he created signals for ILU bypass and load upper immediate bypass. Then he is feeding register file with signals from the end of his pipeline. So he converted a single cycle design into a pipeline design, and you can also see that he is implementing bypasses by feeding to ALU source is like our regular arguments or bypassed arguments using bypass index variable. So he is getting this like immediate value, and then he put like additional always block where he implements this pipeline. In principle, this code could be put into control module. So some like rear CPUs like MIPS microactive UP used in MIPS FPGA educational project uses a module called master pipeline control, like MPC, which handles such pipeline registers, like produces like control signals for it, and then like you can see he is writing into register file using like also this pipeline signal, and by doing this he is able to maximize bandwidth of the whole thing. Yeah, and you can see to his test that his design need less number of clock cycles for a mix of multiplication and LU instructions. And we work with a Mike Kuskov to put it as a sequence of maybe like 5 steps of an exercise. Yeah. So this is my comment on it. Yeah, if like if nobody has any questions, this is probably end for today. But if somebody have questions, you can ask the questions.
All right. I do have a question. Can you show again how you make sure that the memory address is valid in an exercise with delayed memory?
Oh, wait, is it question for me?
Well, I think it's a question for Mike because he's sharing the screen right now.
Yes. Oh, yeah. Let me stop sharing my screen. Yeah. Yeah. So Mike, can you share your screen? Like an answer. This is a question about, yeah.
So the question about latency, fetch latency, right?
Yeah.
Yeah, fetch latency, 1 second. Mhm.
So how does it work? The read valid signal, like we compare the last address with the current, like what's the point?
We check that the address that CPU requests in the current clock cycle is basically the address of what the CPU were requesting on the previous clock cycle, right?
So, all right, yeah, now I get it. Thanks.
Because if CPU will change the address that it requests in the current clock cycle, it means that like it will be already not the valid address. I mean, yeah. So here,
Yeah.
the idea is that CPU will need to keep this address for a couple of clock cycles.
Yeah, I get it. Thanks.
Okay.
We may actually change it because maybe we, well, if we remove this requirement, in this case, we also need to add address valid. So we can have like address valid, data valid, or we can just assume that CPU keeps address for 2 clock cycles.
Yeah, like there are two options.
Yeah. So we can think about like different options, because eventually I want to add here exercises with a full associative cache and with a prefetch in a similar way as full associative cache and prefetch is done in, for example, microchip PIC32 microcontrollers. Like a microchip PIC32 MX has a small full associative cache, instruction cache, and prefetch. And we can do something like this for like our example, because both are very simple. But microchip PIC32 MZ has actually true cache and like prefetch together with this instruction cache, but this is like next stage. Yeah. So eventually we read first a full associative cache, and then we can add direct cache and make some experiments using still school RISC-V to demonstrate different concepts. Yeah, we can actually go pretty far with it. We can use school RISC-V to like demonstrate out of order instruction execution with scoreboarding, like in a classic CDC 6600 design, the first design with scoreboard used in supercomputer CDC 6600 like back in 1960s. So this is one of like textbook examples of out of order. And then maybe even implement Tomasulo algorithm. Because we have very minimalistic base, it is easy to create a synthetic case that proves that we have a performance improvement. And this is kind of usefulness of school RISC-V, that we can demonstrate concepts and make homework. Okay, so any other questions?
So do I get it right here, Yuri, that what you're doing, if I look at the commit for the homework for 5, it's about, I don't know, maybe 40, 50 files, right? And the only comment is add homework 5, right? And then we're supposed to go in and replicate all that stuff that you just showed, putting in all those little bits and pieces to add that additional functionality of the multiple access memory and the multiplier and all that stuff in this class. And we're supposed to go through all these files and add that, right? Is that the idea?
What you do is that there is a baseline example. So first you use to baseline example.
What is the baseline example? Where's that in the Git code? Did you do a separate check of
it
that?
is here, yeah. Let me show you this baseline example. So if you go to system verilog homework, oh wait, it's not here.
That's the Git repository I'm looking at.
Yeah, 1 second.
The thing is that
so
we have.
If you go to, let me show you a baseline example.
You can come back to Philip repository.
Yes, no, but I'm not sure whether he's up to date. So if you go to,
I could see the 5 homework that was added.
Yeah.
2 weeks
so
ago.
this is a baseline. So here, this is a baseline, and baseline has like those like bits and pieces, but you need to study this like complete CPU, and then you need to copy this code, and then go to
And what do you talk about this code?
yeah. So then you go, for instance, in 0508.
We don't
And
see, like, we see the DVCA
Ah.
private.
What?
Probably you need to switch window you are sharing, no? Or we
Maybe yeah.
see
Oh,
the code of private.
yes. Probably I need to switch window. Okay. So do you see private, or do you see Windows instructions? So what?
Private.
Just a second. Oh my God, it's did something wrong. 1 second. Let me.
So private is where you're putting the solution, right?
Yeah,
Let
like
me.
we have two
Yeah.
repositories, and
Let me
I
close
was
everything.
sharing the private repository with solutions, and Yuri will show
Right.
the public repository with only like definitions of exercises.
And that's mixed in with that huge chunk of code that describes the whole RISC-V chip to start with.
This is not really huge. This is 200 lines. 1 second. Why it shows private? Yeah, because I opened. Okay, let's close this one.
I don't see anything, Yuri.
Just a second. 1 second. 1 second. Let me show you. Where did this Zoom got this file? Just a moment. What if I share desktop? Nope. Just a moment. So what if I share my screen? So what if I share screen here? Okay. And now what if I stop sharing? Okay, now what if I stop share? Okay, I stopped sharing. Now let me share this screen again.
Okay.
Just a second. I will share the screen. Oh, okay, yeah. So this is yeah. So this is the system Verilog homework. So if you go to 055 and single cycle CPU, you can see that there is a CPU baseline. And in the CPU baseline, there is this whole design. So basically, because this is homework part 5, by the time people go to homework part 5, we assume that they already understand basic mechanics of Verilog. So like syntax and like a combination and sequential construct. So by this time, they are supposed to be able to handle designs of like 200 lines of code. So this is not the stage where we have just a small, like a few lines of code exercises. So there is this whole design. So they need to actually study it, and once people study it, then they need to make some small changes, and
Right,
essentially
but
here.
what I'm wondering about is how are we supposed to figure out how to make those small changes? And it seems like the clues could be in the git commit that you did for the homework, but I always see is add homework 5 and then this massive commit. It
No,
seems
no,
like it would be good if
there is a
more hints were in here.
description here. Wait, Mike, did you write instruction? What they have to put here? Did you write anything here?
I didn't add instructions inside, but there is a big file with instructions in Russian.
Oh,
So,
wait,
so I can
you
translate.
need to write this instruction in English, because
I should learn
I
Russian
put
first.
I put a brief instruction, but for yeah, so like basically this is the last part of examples, which is now still in a process of being created. So like I put some like skeleton and I put solutions for 5.1, 5.2, 5.3, 5.4, 5.5, 5.6, and I put CPU baseline. And after this, I gave to Mike. Then I put solution for 5.12, and after this, we discuss with Mike, and this is actually what we are discussing right now. We discussed with Mike different solutions for this exercises. So he just presented his solutions, and I show a solution of one students. I was like screening by me like personally for the interview, kind of non-official. This is just my like personal screen when people like contact me. Like ask them to do some like exercise, and like one like person did this exercise and created pipeline design, which is like very impressive, um, uh, comparing with very many students who actually don't do this. And so we are now in a discussing of putting solutions for the homeworks from 057 to 0512. And one thing which has to be implemented, we need to write instruction how to do this homework. And Mike put this instruction in Russian, so he can put this instruction in English, or somebody else can also put this instruction in English. So if somebody can like volunteer,
I can
this
translate
is
it
a code
using
editor project. Huh?
GPT. I can translate it using GPT and just fix the
GPT
typos.
creates very like unpleasant text. I personally, once I detect GPT, I immediately stop reading and just close this thing. So somebody need to put it in like nice English, which is like alive.
I think
Yeah.
I can do it.
Huh?
I think I can do it
Maxim? Yeah. Okay.
manually.
Okay. Let's yes. If you can do it, let's do it. Yeah. So you can work together with the Mike Kuskov and create instruction for this 0, 5, 8, 9. So 7, 8, 9, 10, 10, 11, 12. Yeah. So we need
Yeah.
to do this. Yeah. Speaking of, do you have Alexander? Yes, Alexander Ryabov. Like already got disconnected. He put instruction for going, but we didn't finish it yet. Anyway, okay. So let
Anyway,
me
I'm thinking
write
that
down
we're
that
missing an
Maxim can.
opportunity. I think we're missing an opportunity to make it easier for students to assimilate this information, to put a lot more information in the Git commits instead of one big blob. It seems like it should be more structured and educational than just, it's like checking in, a whole architecture into the Linux kernel and you got 500 files. And what they wanted, it the Linux kernels, each piece had to be checked in individually with separate commit messages to give people the ability to follow the logic of the whole thing. And I think big massive
commit.
check-ins is making it difficult to appreciate the complexity of this chip and the design and what all the pieces are doing, right? Seems like all the history's gone.
First of all, this particular repository, which is public,
I'm talking about the
it is
last
not
commit right
supposed.
now that Mike did. I'm talking about the last commit
Yeah.
of the add homework 5. That one commit.
No. Let me like explain something. There are two repositories. One is private and another is public.
Right, I'm talking about the homework one. The one
Yeah,
we
this is homework. Homework has two versions. One is public and another is a private.
I understand that.
Yeah.
I'm talking about the one we can see about the add homework commit we missed an opportunity to make it much more easy to
But
understand what all this stuff's doing and how it's all linked together by making one big massive commit and no message other than add homework 5. It seems like
It's a
we're
tech.
trying to be educational here, so we should be very verbose on the educational aspect of the project.
Okay, so like Pete, let me explain you first how like it works. How it works? First, we have a private repository which nobody can see.
I know.
So this called system Verilog homework private. So there are like few people who have access and people who create exercises. Okay.
Okay.
So now, if you go here, you can see that this file, like this, like baseline CPU, has actually many small commits. So if you go to history of, like, let's say, like CPU, like, let's say, like this file. So let's get a history of this file.
I thought we're not supposed to be accessing this route because this is
Yeah,
giving.
this is my point. So here we have the whole history of commit. However, then we have a script which automatically generate public repository by removing solution pieces to make empty files, so that
I guess you can show this
students can
script.
start. Huh?
Show this. Show the script.
Yeah, let me show you this. Let me show you this script. So this script is called prepare public package. So this script checks that we don't have like tabs and like many like other stuff, and then at the end, what it does, it uses sed to remove all solution pieces. Okay. Now we do put in comments things like to do. So for instance, if you go into like combinational logic, like let's get the very first exercise. In the very first exercise, we ask to do using code for
Yeah, I know.
max
I've
2 1
been
as an
following that.
example, and then I
Right.
put start solution. So we remove like all this stuff, right?
Mhm.
So now we don't run this script like every moment we do a small change. So for us, we are in different situation as a Linux kernel. In Linux kernel, we do need to look to the history of commits to see for the logic what is going on.
So what
So
you're
why
saying
people
is
added feature?
these start solutions are peppered all over in the in this add homework 5 commit. If I was to do a git grep for start solutions, I would find all the changes.
No, you need to grep not for start solution, you need to grep for to do, because this
To
code
do.
does not exist here. Student has
Right,
to
right,
write
right. Okay.
this
So
code.
I
So
grep for
you
to
need to
do.
do grep, you
Grep
need
it.
to do grep to do. The problem is that right now, the solution for CPU is not very well documented with this to do,
What?
because this is still work in progress. Okay.
So you're
So
not you're not ready
discussing.
for students to do this homework 5 yet. Is that what you're saying?
Yeah, like only like students who work with like a mic, like in like Russian universities, they have like his file with his instructions. But this happened only recently, like 2 weeks ago. So like basically for the rest of students, we don't have this section 05 ready at all. So now we need to create.
So then shouldn't that be in the commit message? Add homework 5, not ready for prime time or something?
But
Yeah,
like it's
maybe I can put this into commit messages, but we simply do not try to put this into commit message. So like basically, if you look to
Well, we're trying to
like
follow
Mark's,
everything, and it seems like that's an
the
awfully terse message for such a huge block of code to be
yeah,
checked in. And it would be
He
easier
put
for us
this
following
whole
it if we had a
instruction,
lot
you
more
see?
information.
Yeah.
So the problem is that our Russian students, we have around 100 of Russian students, and for them, we explicitly say that please follow the document, like read carefully the document, and only after that you can start the solutions. And basically, all my local students, they firstly read the instruction, and only after that they understand what to do. For English speaking students, we will just in progress. So it's kind of 50-50 situation.
But couldn't we make it easier by putting a lot more information in the Git commits? Just like normally when you're developing code and following other people's work, you use the Git commit history to follow everything?
But why history is like even relevant here? Because when we do changes, we don't do changes in a certain logical sequence. We do changes in one example, like I do changes in one example, Mike is doing changes in another example, and we are doing this like out of order. So and then we do changes, we go back, do change, so we rewrite on multiple times. And for students, it makes no sense to show history, to follow history of changes. Students need
Right,
to
but
follow
that's like if you're
logical
making a
sequence.
change to the Linux kernel, you work in your own repository, you get it all cleaned up, and then you make a series of commits which are piecemeally, bite-sized so that people can understand it. You work locally, you do all your stuff locally in your local Git repository, right? And then you condense it down to a small set of commits for people to follow, right?
Yeah, but in this case, they see just a bunch of to-do messages. This to-do is saying them that you insert this code here, you insert this code there.
And
And
also
baseline is a compact enough baseline is a compact enough, so we don't need to have a series of commits to explain what the CPU does, because we have the whole presentation about it in the many slides.
And also in Linux kernel, we don't have private files that are not shared or not checked to the public Git. Because in homework, we have a series of commits that change the solution, which will be excluded. And for students, students will see 10 commits without any changes because we changed the solution, which is excluded.
So the baseline files I'm looking at right now in the Git commit, this is the stuff that is relevant to the homework project, is that right? Baseline? What's the meaning of baseline?
So baseline is a baseline for the series of exercises. So we have here exercises, so 5.8, 5.9, 5.10, 5.11, 5.12, and these 5 exercises, they are incremental changes on the top of CPU baseline. So first you study what CPU baseline does, and then you follow instruction and to-do message to put additional code into 5, 9, 10, 11, 12, and so on.
Right, like right now I see the Fibonacci example. It's in the instruction ROM code, right? I don't see any to-dos in it though. So
yeah, you don't see any to-dos because we don't need to. Oh wait, you're talking about
I'm looking
this
at the
file.
baseline code right now in the Git repository.
Yeah. In a baseline code there is no to do, because baseline is not supposed to be changed. Baseline simply baseline is a simply baseline. So this is something you need to study, and you don't do anything with it. This is just an example.
So how does
It's not
CPU
supposed to.
baseline fit into all the rest of the CPU code? There's CPU with combo, CPU with multiple latency.
So you start with files in CPU baseline, and then based on instruction and based on to-do commands, you are supposed to make changes in all these files. And Mike can put additional comments you want to do such changes. For instance, he may put a comment that inside decode you need to add something like here, like add additional like a jump type instruction or something, and then put into like a SAR control something like add additional statement to reflect control. But the but actually, I don't think we need to put too much comments here, because the whole point for doing this particular exercise for the student is based on his understanding of baseline CPU. He need by himself to determine and do it by trials and errors to add all components so that final test works. So because this is like already exercise for people who learn the basics, we now expect him to find what has to be changed. Don't micromanage him, like type this line here, type this line here.
Okay,
This actually
challenge.
kind of advanced exercise. We don't need to like micromanage here. We just need to put correct instruction and put like a high level description of what has to be done. And then he can self-check himself by simulating it together with a test bench. So this test bench just checks that.
Right. Yeah, I got that part.
Yeah, this like test bench just checks that
Just like the other
we
homework.
like eventually get we like eventually get a certain value in certain register.
Well, hopefully that Russian document will be translated to English by the time.
Oh yeah, yeah.
Why?
This is something which we need to do like right away. Yeah. So yeah. So like Maxim says he will do this. So yeah, let's Maxim do this.
Yeah, I think I can finish it by tomorrow.
Oh great. Yeah. So just wait. Are you added to private repository?
No, I'm not, but I think I can just make a pull request to public.
Yeah, you can do it this way if you want. Yeah, okay, and then we can propagate it to private, or like I can add you
But I guess Maxim is
private
also,
as well.
Yuri, I guess Maxim is one of the students who is solving the homework. So, like, I guess it's
Okay,
better
yeah.
for
So
Maxim to solve the solutions, like get the solutions by himself for practice.
yes, absolutely.
What was that? I
So
didn't
just like
understand.
add to public, and then we deal with it. Yeah.
The Russian document doesn't do any good being translated to English if it's not made
Oh
public.
yeah, absolutely. Yeah, and maybe Maxim can put some more details, give some additional tips there. Maybe like I will also put some information, just like yeah. So
Yeah,
like basically we are now preparing sort of like draft version of these exercises, and we are going to like enhance these exercises within a year to like include multi-bank like multi-memory bank exercise, some exercise with CPU exchanging messages through FIFOs with like cache coherence, maybe even in the future, like in 2 years and so on.
oh, actually, I have another proposal about an exercise with the B instruction. I think that maybe we should change the task to specifically say that we have to add a jump and link instruction, because if we say add a pseudo instruction, it just obfuscates the task for no reason. Because you look at the documents, RISC-V, and you don't see this instruction, you have to figure out. It's just
Yeah,
annoying.
but actually this is the fun part, because by looking at it, students can find out what is pseudo instruction, and then like deducts to implement pseudo instruction, we need to implement real instruction. And now the question is that should we implement real instruction just enough to pass this test, or should we implement jump and link instruction completely? And if you implement jump and link instruction completely, we may have like another test which actually calls function using jump and link instruction. So here we can create like two exercises. One, we just put J, and this is up to student whether he implements a restricted version of jump and link, which only works for zero argument, or whether the student implement complete JAL instruction which can be used to call functions. It's up to him, and basically in both cases he is right, because the task was defined in an ambiguous way. And after this, we can have another task, which is to implement jump and link instruction and JR jump using register to implement function call. And then we can, and then we are talking about example which has function calls to like call function like factorial with different arguments. This like can be like another task.
Yeah, all right, I see. Fair enough.
Yep. Okay, yeah. So Maxim, this is great idea. So please write this instruction, and then we. So basically, this set of examples is just a starting point. We need to develop them into a much larger tree of examples and problems. And this is not something we can do like in a day. This is something which can do for like several months, and add to like a instruction cache and prefetcher to it and so on. But eventually we can create a comprehensive set of examples starting from a simple baseline. Okay, so any other questions right now? So if no questions, so thank you everybody, and see you next time. So same time next week. Yeah. Okay. Bye-bye.
Same.
Bye bye.